Hello everyone, my name is Joseph. I'll be going over Griffiths Problem 1.57, where we're asked to compute the line integral of this vector field around the path shown in this figure, and we're asked to do it in cylindrical coordinates or in spherical coordinates. We check our answer using Stokes' theorem. So, Stokes' theorem tells us that the closed path integral is equal to the flux integral of the vector field's curl over the surfaces. So let's start by calculating the closed path integral. We can split the closed path integral into its components, or into its separate paths. In this case, it's A, B, C, and D. And starting with A, I stuck to spherical coordinates. So for path A, we note that our r goes out from 0 to 1, our theta is constant at pi halves, and our phi stays in the x-axis, so we stay at phi equals 0 and d phi is equal to 0. So when I write out the general elemental path in spherical coordinates, for path A, we simply get dr r hat. After dotting our vector field with elemental path, we get the integral of r cos squared theta dr from 0 to 1. And after evaluating this integral, it simply evaluates to 0. Moving on to path B, we note that our r stays constant at r equals 1. That means our dr is 0, and that part of the elemental path will go away. For theta, we also stay at a constant, theta equals pi halves. Phi changes. Phi goes from 0 out to pi halves. So our elemental path is simply r sine theta d phi phi hat. And after dotting our vector field with our elemental path, we get 3r squared sine theta integral from 0 to pi halves. And after evaluating this integral, we simply get 3 pi halves for path B. Moving on to path C, it gets a little bit more complicated. So our r starts at 1, but then we end up over here, and we don't know that exact value yet. But we can solve for it, since we know we start out here and end here. We know the legs of the triangle. We can use Pythagoras to get that radius. So our r goes from 1 to the square root of 5. Theta, well, our theta starts at pi halves, and we end at whatever this angle is over here. I marked it as theta final, theta final. And we can use tangent, since we know the length of this and the length of this, we can use tangent to find that angle. So our theta goes from pi halves to this angle over here. This entire path stays in the YZ plane. So our phi stays constant at pi halves and d phi is 0. So for this path, path C, our elemental path is dr r hat r d theta theta hat. After dotting our vector field with our elemental path, we're left with r cos squared dr minus r squared cos theta sine theta d theta. We can't quite integrate this yet, because as we go along the path, our r changes and our theta changes, and they are interrelated. So what I need to do is I need to find an expression that lets me write r in terms of theta. So as I walk up this path, my theta is changing and so is my r. But this leg right here stays constant. So I can use, so I can write a relationship between theta and r using sine. The sine of this angle is 1 over r. And solving for r, I get r is equal to 1 over sine theta. And I need to find what dr and d theta is, so I take an implicit derivative. And that gives me dr, after solving for it, that gives me dr is equal to minus cos theta over sine squared theta d theta. So now that I know what my dr is, I plug them in. After plugging in, I get this integral. Now everything's in terms of theta, and I can start solving for it. The sines here combine to get sine cubed, and the cosines combine to get cosine cubed. And this sine cancels with one of these signs here, so I get cosine minus cosine over sine d theta. So I get minus cosine over sine d theta. I can pull out the negative. I would like to combine these two terms. So I turn this 1 into sine squared over sine squared, which this is just equal to 1. So now my integral simplifies to cosine theta over sine cubed theta. We can integrate this with the u sub by letting u equal sine theta, giving us du is equal to cos theta d theta. After substituting, integrating, and replacing my u back with what it was, and after evaluating, I'm left with 2. Moving on to path D, we found that the r was the square root of 5, and we go down to 0. Our theta actually stays constant at the angle we saw previously, which is tan inverse of 1 over 2, meaning our d theta is 0 since it was constant. And our path stays in the yz plane, meaning our phi is pi half, which is also a constant. So then my elemental path is just dr r hat. When I dot my vector field with my elemental path, I'm left with the integral of r cos squared theta dr from root 5 to 0. And after evaluation, I get -2. So now I have all my path integrals from a, b, c to d, and together they make up the closed path. And after adding them, I'm left with 3 pi halves. Now we're not done yet. Now we need to verify this with Stokes' theorem. So first, I need to calculate the curl of the vector field. The curl of the vector field in spherical coordinates is given by this equation. This is the r component of the vector field, this is the theta component of the vector field, and this is the phi component of the vector field. I plug those components into here, where it says it AR. And after evaluating the derivatives, doing some simplifications, I am left with 3 cotangent r hat minus 6 theta hat plus 0 phi hat. And you can pause for the details. So now that I know the vector field, now I need to figure out what surfaces I will be integrating over. This is not exactly one surface, but what I can do is I can split it into 2 surfaces, surface S1 and surface S2. And I can do it by adding, by splitting it with 2 paths going in opposite directions of each other. And this won't affect the total line integral because since they're in opposite directions, their path integrals will cancel out. Starting with surface 1, we must find the bounds. And the bounds for this, our r goes from 0 out to 1. Our theta is actually constant since this lies in the xy plane, and this will be important later. And our phi ranges from 0 to pi halves. So an important question is, what is the orientation of the surface? And to do that, we use the right-hand rule. We get that our normal direction is in the z-hat direction. So now the next question is, what is my elemental area? So I can draw a little chunk by changing d phi and an extra chunk by changing dr. So this here is my area. If I draw out this chunk in the limit that my dr goes to 0, this looks more and more like a rectangle. So to get the area of this, I multiply, just like a rectangle, and I get r d phi dr. And to turn it into a vector, multiply it by my orientation vector, and I'm left with r d phi dr z hat. But the z hat is a Cartesian vector, and I'm trying to integrate this in spherical coordinates. And then I need to convert z hat into spherical, and this is how to convert. For this area, my theta was pi halves, so when I plug in theta, I get z is minus theta hat. For this area, z hat is minus phi hat. So I will evaluate that integral. So for S1, after dotting my curl with my elemental area, I'm left with the double integral of 6r dr d phi, and after evaluation, I'm left with 3 pi halves. But I'm still not quite done. I need to evaluate the second part of the flux. So the second part is this region in this case. And I note that our r also ranges from 0 out to our maximum, which is root 5, and our theta ranges from 0 to what we found previously, tan inverse of 1 over half. And our phi, in this case, is pi halves, and that is also important and will come up later. So what is our elemental area? By the same arguments as before, our d area is a quote-unquote spherical rectangle, and it becomes r d phi dr. And what is the orientation? Using the right-hand rule, our orientation is in the x-hat direction. So the thing is, x-hat is a Cartesian vector, and we need to convert it into spherical coordinates, and we can do that with this conversion. You can refer to Griffiths on how to convert from spherical to Cartesian. Remember, our phi was pi halves. After plugging my phi into here, I get that my x-hat is equal to minus phi hat, so I'm left with an elemental area of minus r dr d phi phi hat. And after dotting my curl with the elemental area, this entire dot product is 0. When I add both of my fluxes, the flux over surface 1 and flux over surface 2, I get 3 pi halves, which is also what my path integral worked out to be. So Stokes' theorem works, and our answer is verified. Thank you.